Okay, so today we'll start with lesson 5, and what we will be keeping in mind on lesson 5 is bond polarity using the dipole theory, and then classifying compounds based on the bond polarity, and what are the inter and intramolecular forces within the compound. So now we touched a bit on the dipole theory, but let's kind of review and recall what we have done and what we have said in terms of the dipole theory. So a dipole moment is describing first of all, in a compound is with an arrow that looks like this. And the direction of the arrow is telling us what is the direction in which the electrons are mostly staying on, in which atom the electrons are staying more. Because what we said in terms of the electronegativity is that the electron, some atoms have a higher electronegativity in comparison to the other atom, and when they are combined together, the electrons have the tendency to stay more into that atom that has higher electronegativity, and this is creating a slightly positive and negative polarity in between the atoms. So a dipole moment describes the direction of the negative pole in the molecule, okay? So where this arrow is going to, then what we have is we have a slightly more negative atom, leaving the other one slightly more positive, which will create that is known as the dipole moment. Just because there are polars, though, polar bond in a molecule, that doesn't mean that we will have the molecule itself will be a polar molecule. Okay, so when the reason is because you can have one dipole moment that goes in this direction, and then you can have on the same compound, you can have a dipole moment that goes in the other direction, leaving this slightly positive and this slightly negative. So on the same molecule, those two will cancel each other, making it a non-polar. So the fact that there are polar bonds doesn't mean that we will have a polar molecule. Okay. So now factors that affect the dipole of the molecules are electronegativity of the atoms in the molecule. Okay. Next one is the bond dipoles. That affect the net dipole of the molecule, as we said it here. So you can have two dipole moments, but since they are in the opposite direction, then they may not be a net dipole in the molecule. And then the other one is the shape of the molecule, the Vesper shape of the molecule. The Vesper shape of the molecule. Okay. And what do you have to keep in mind? That bent and triangular pyramid shape will always be polar. Okay, because the reason is because that if it is bent, then the two dipole moments will definitely have a component that is not cancelled out, creating one vector that goes, or one dipole moment that goes up, or up or down, doesn't really matter, but there is a net pole, net dipole moment that is created, because you have one that is going this way, one that is going that way. So the sum of the two will be the same as saying this plus this. So the sum will be the net dipole moment will be like this. Molecule is considered to be non-polar if and only if, so you should, there is no others that if they are dipolar. There are 4 valence electrons in the central atom. Exception is a boron, that will be 3, and that are bonded at the same element. Okay, so for boron we will have 3, but in general will be 4 elements that are bonded at the same, at the 4 valence electrons that are bonded to the same element. So examples are CnCl4, SnCl4, methane, carbon dioxide, and boron trifluoride. And then the atoms that have the same type of elements. So pretty much the polyatomic atoms. Okay, so what I want you to do now is to take a look at the textbook, if you have the textbook. Okay. Take a look at the textbook, page 99, and you will see a table which is very self-explanatory. You will have a polar molecule if you have a different diatomic with 2 different atoms, or if you have nitrogen and other atoms, so 3 other atoms, or if you have oxygen and other atoms. So let's say this is a bent one, or you have the oxygen that is with chlorine on this case, and you have carbon that is with 2 or more kind of different atoms. But when we have a non-polar, then we have all the polyatomic elements, like gases, as we have said, hydrogen gas, oxygen gas, fluorine gas, and so and so. And then carbon that is connected with 4 atoms of the same type. So let's take a look now to those examples that are here. So the first one is boron trifluoride. Let's start by drawing the dipole or a structural diagram of this. Now boron, since it is in an exception and it needs 6 electrons to be satisfied, the structural diagram will be something like this. Okay, so now boron is satisfied and fluorine are satisfied, and if you do this the Lewis dot diagram or the Lewis structure diagram, then you will see that this is what the structural diagram is. Now, based on the electronegativity of each of them, we can say that the dipole moment for the boron and one of the fluorines will be in this direction here. This has no brain because fluorine is the highest one, so we don't even have to look at the periodic table. And For the other fluorine is like this, and for the third fluorine is like this. Okay, so now what is happening here? Those two, let's say 1 and 2, are forming, or the net of this is something like this. The net of 1 and 2. So 1, 2, and if we call this 3, then we will have, and then 3 and the net of 1 and 2 is cancelled out. So then this result to be a non-polar molecule. Let's take a look at the dicarbon dihydrogen. Okay, so let's draw this is the case when we have multiple central atoms. So the structural diagram will be carbon here, and then 1 hydrogen in one side and 1 hydrogen on the other side. Okay, so now based on the electronegativity of carbon and hydrogen, we can say that the dipole moment is going like this between the two, and the electronegativity between those two carbons is, the difference electronegativity between the two carbons is 0, so we don't have a dipole moment on that case. And if we say that this is 1 and this is 2, then we can see that the two that are with the same value going on the opposite direction, the will cancel out. Okay, will cancel out, making no net dipole moment, which will result into having a non-polar molecule. Okay, so now let's see and observe what is happening to dihydrogen sulfate, monosulfate. The structural diagram of this will be sulfur, and then hydrogen and hydrogen here. Okay, so now if we take a look at the difference of electronegativity, we will see that it is towards sulfur. So will be the dipole moment for this will be in this direction, and dipole moment for this will be on this direction. So those two, when they are added together, we will have a net dipole moment that goes like this, which means that those two will not cancel because we have a component in the vertical direction that do not cancel out. So then we will have a dipole net. This is the dipole net. That will result making this molecule as a polar. Okay. The same idea is on the case when we have phosphorus trichloride. So the structural diagram in this case will be phosphorus at the top, and then we will have 1 chlorine on this side, 1 chlorine on this side, and 1 chlorine on the other side. So it is a pyramidal triangular shape that we have in terms of the Vesper diagram here. So then if we take a look at the dipole moments that we have here, phosphorus is a 2.4 and chlorine is 3.2, so it is towards chlorine. So we'll have a dipole moment that goes like this. for all of those three. And then that means that those do not cancel out. So you have 3 on each direction. They are the same values, but they do not cancel out. The dipoles will not cancel out, creating a net dipole. That means that we will have a polar molecule. Okay, miscible versus immiscible. Therefore, so now what it is says that as miscible is like dissolves like. This is what it's saying. Okay, so now what does that mean? It means that a polar will dissolve a polar molecule, and a non-polar will dissolve non-polar molecule. So then if you have a polar molecule, will dissolve a polar. If you have a non-polar, will dissolve a non-polar molecule. But when we see that is immiscible, that means that don't mix likes, dislike, likes, likes will not be mixed with a non-like. So that means that non-polar will not mix with a polar. Let's say water will not be mixed with oil, which is non-polar. Okay, so now we'll stop the video here and complete the assignment for this part of the lesson. And it's this one here. And we will move to intermolecular and intramolecular forces in a molecule and in a. So we have two types of forces that we have to discuss: intramolecular forces and intermolecular forces. When we are talking about intramolecular forces, what we are discussing the forces within the molecule. So those are forces that are between atoms in a molecule. If we have, let's say, CH4, the forces between, so as structural diagram, this is CH, H, and what it is actually is a tetrahedral shape. So the forces between carbon and hydrogen are called intramolecular forces. So they are between atoms in a molecule that will result in the chemical bonds. So the bond between those two. We are not talking here the forces between the hydrogen, because the hydrogens are not bonded together. So the bond is happening between carbon and hydrogen. So therefore, this is the intramolecular forces that we will see. Okay, so in methane, the bond between carbon and hydrogen is considered to be intramolecular forces. Okay. When we see the electronegativity between those two forces, so then between those two atoms, sorry, then we will see that the electronegativity difference is about 0.4. That will make it to be polar covalent bond characteristics. Okay. Now, when we talk about the intramolecular forces in the ionic compound, keep in mind how the ionic compound are formed. What we have in the ionic compound is the exchange of the electrons, which means that one entity is becoming positively charged and the other entity is becoming negatively charged. And what is happening between those two is an attraction force, which is the electrostatic force. Okay, so in the ionic compound, as the intramolecular forces that is keeping this compound together is the electrostatic force. This type of force is the strongest one. The strongest type of forces on all the forces that we will discuss. Okay, so what is happening here in terms of the electrostatic force? We say that the general law of the electrostatic force is that opposite charges will attract and same charges will repel. In this case, since we have two opposite charges, they will attract each other. Okay, so now intermolecular forces are forces that are in between molecules. Okay, so our forces between molecules. If intramolecular forces were forces in within the molecule, intermolecular forces are forces between molecules. What is happening in between molecules? Those forces are the forces that cause the molecules to attract each other. Okay, so they are attracting each other, to attract each other. And in this way, what is happening, they are a solid or a liquid is formed. Solid or liquids are formed. Okay. Because what is happening is the molecules are connected together. And now we know, even from lower level of sciences, that when those molecules have a certain connection in between them, then the state of matter will be a solid if they are very close together, and will be liquid if somehow there is a force in between the two. So now let's take a look at the water molecule, which is a polar molecule. Therefore, why? Because it's bent. It's bent, an angular bend shape. So now what will happen in the water molecule is something like this between the water molecules. So we have an oxygen here, and then we have two hydrogen here. Okay, now based on the dipole moment, what we see is that we have a dipole for each of them, leaving this as the delta negative and this as a delta positive, delta negative, delta positive. Now, what do you see here? You have the oxygen is a delta negative, which means that the electrons are spending more time in the molecules, in the atom of oxygen. So now, what is happening though is that we have another molecule here, oxygen, hydrogen, hydrogen, another molecule here. And on this molecule, the same thing is happening in terms of the dipole moments, leaving the hydrogen slightly positive and making this slightly negative. Okay, so this is negative, positive, and this is negative. Okay, now this slightly negative atom, that is oxygen, of this first molecule, let's say, attracts this hydrogen, which is slightly positive, because negative and opposite charges will attract each other. Okay, and this is the intermolecular force between the two. Now, let's suppose that we have a third molecule here. So we have oxygen here, and we have two hydrogens, hydrogen and hydrogen. And the same thing is happening here. Dipole moment is toward the oxygen, leaving oxygen slightly negative and hydrogen positive. So now what is happening, that this oxygen is attracting that other atom of hydrogen and creating this intermolecular force here. So the partially negative pole of one of the molecules will attract the partially positive pole of the other water molecule on the creating the structure of everything, creating the liquid state of water. Okay, so let's talk now about the types of intermolecular forces. There are three types of forces that are known as the intermolecular forces, so forces between the molecules. The first one is London force, which is known as LF, the convention that we use. This is present in all molecules. And when I say all, doesn't really matter what it is, in all molecules and atoms. Okay, so it is everything. Everything that has an electron experiences London forces are the weakest one. Those are the weakest one. Let's get this. The weakest force in the group of forces, and it's created as a result of temporary uneven distribution of electrons. So what is happening, even when it is non-polar, what is happening is that one of the atoms sometimes has more electrons than the other one. And then in this case, even when we have non-polar, in this case, what is happening is a slightly positive and a slightly negative difference between the charge between the two atoms. And this is creating the London forces. But this uneven distribution of electron is very temporary, because we are dealing with a polar or non-polar, even polar or non-polar, doesn't matter, molecule. So since it is temporary, then this force is temporary as well, okay? But exists no matter what. It It exists on every single molecule. Okay, next one is the dipole forces. Those type of forces are present in polar molecules only. In polar molecules only. This is stronger than London forces. So if we are saying that this is the weakest is number 1, then this will be number 2. Stronger than London forces. And is as a result of the permanent uneven distribution of electron. Because we have, in this case, we have a net dipole moment. Okay. The third type of force, which is the strongest one, is the hydrogen bonding. It's known with HB. Is as a result of the permanent distribution of electrons. So permanent distribution of electrons, and it is known as, so it is the bond created between fluorine, oxygen, and nitrogen. So with hydrogen. Okay, so when fluorine and hydrogen are bonded directly, or oxygen and hydrogen are bonded directly, or when nitrogen and hydrogen are bonded directly, then what we have is that is known as the hydrogen bond. And this is the strongest one, the strongest bond. The strongest force between the two, all of those 3 forces. In a general name, those forces are known as van der Waals forces, which is a scientist that was studying those forces. Okay, so let's take a look now to this example that we have here, and we will see and discuss the type of forces. In this case, we will do even a short review of what is the Lewis dot diagram, what is the shape name, and how does that look like, Vesper, polarity, and then see what type of forces do we have. Okay, so let's see, the first one is the Lewis dot diagram for this compound. What do we have is nitrogen is at the top, and then we have hydrogen here, hydrogen here, hydrogen here, and then we have 2 electrons and lone pair. The shape, based on what we have said even before, is triangular pyramid. The shape name. The shape with dipoles will be nitrogen will be here, then we'll have hydrogen here, we'll have a hydrogen here, and we will have a hydrogen here. Okay. Now the dipole moment will be between nitrogen and it will be towards the nitrogen. So dipole will be like this. As you see, there is a dipole net, and the dipole net is in this direction. So then that means that we are dealing with a polar molecule, and without even thinking what is happening in the molecule, you just say London forces, all of them have it. Okay. However, since we have a dipole difference between, or a dipole moment between N and H, then we will have a dipole-dipole force. Since we have a hydrogen and a nitrogen direct bond, then we will have the hydrogen bond as well. Let's take a look at the other one. So we'll have OCl2. Now the Lewis dot diagram for it will be oxygen. I will write it here. Oxygen is here, and then we'll have two chlorines, so chlorine and chlorine, and we'll have single bonds, and then we'll have the chlorine field with 8 electrons. What is happening here? If we take a look at the shape, what we will have is oxygen and chlorine and chlorine. Then we will have 2 electrons that are here, and the difference between the two will be, or the dipole moment will be this one here. So it's a bent one because we have those lone pairs, creating a net dipole in this one, in this direction, making it a polar molecule, which gives us the bent shape or angular bend shape. And as I said, we don't even think if there is anything in London forces or not. We just check it out, and then we see there is a dipole moment in between the two molecules. Yes, then we have a dipole force. There is any direct bonding between hydrogen and fluorine, oxygen, or nitrogen? No, so then we don't have the hydrogen bond. Let's move to the next one. So we have silicon tetrabromide, and the Lewis dot diagram will be silicon being the central atom with 8 electrons in the surrounding, and then we'll have 4 bromines that have 8 electrons in the surrounding. Okay, their shape is tetrahedral. Tetrahedral, and shape name, and the shape with bond dipoles will be silicon here in the middle, and then we'll have 1 bromine here, 1 bromine here, 1 bromine here, and 1 bromine here. Okay, so if we see the difference between bromine and silicon, then we will see that the difference between the two is toward bromine. So the dipole moment will be this, 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 and this one here. However, since this it's always going is the same atom that silicon is bonded with, and the difference in electronegativity is the same, and they are in 4 directions. This will make it a non-polar molecule. London forces exist no matter what. Since it is non-polar, then we will have not a dipole-dipole moment, and since hydrogen is not even present here, but is not connected or bonded directly with fluorine, oxygen, or nitrogen, then we don't have any. And so now we have CH2O, and the Lewis dot diagram for CH2O will be something like this. Carbon is here, then we have a double bond with the oxygen, and then single bond with the hydrogen. And then the shape is triangular. No, trigonal planar, trigonal planar. Okay. Planar, which is something like carbon, hydrogen, and oxygen here. And when you do the electronegativity difference between carbon and hydrogen and oxygen, then we will have a polar molecule. As I said, we always will be having London forces. London force no matter what, but since now this is polar, then we will have dipole-dipole forces. And in this case, even though that we have the hydrogen and oxygen, which completes the condition to have hydrogen and oxygen, but since they are not directly connected between each other, then what do we have is we do not have the hydrogen bond forces. So even though that hydrogen and oxygen are part of the molecule, since they are not directly bonded between each other, then we do not have the hydrogen bond here. Okay, I hope that this is clear. Okay, so now let's move to the other one. So we have HCN. What do we have here in terms of the structural diagram? Is carbon is here, and then we have nitrogen on one side and hydrogen on the other side, and we will have a net dipole that goes toward the nitrogen. So then what that means is that we will have London forces and we will have dipole forces, since hydrogen and nitrogen are not directly bonded. Then we will have not London, hydrogen bond here. And on this next example, what do we have is sulfur, oxygen, and oxygen in one of them is double bond. So we have lone pairs as well. So then what we have is only London forces. Okay, so now for this lesson. Continue with the assignment that we have here. This is repeated twice, I think. And then we move to this one here. Please consider what is the intermolecular forces in terms of which one is the strongest. And that's it for this lesson.